All right, my friends, happy Monday. There we go. So, as I think I said last week, in addition to the premiere of The Mandalorian, you guys have an exam tomorrow and the next day. Your questions about the exam have typically been, how hard is it? The answer is extremely hard. It's not funny. You can't joke about these things, right? Okay. No, so it will be about as difficult as the kind of problems you're facing on the practice exam. Now, the issue on everybody's mind is how much of chapters 7 and 8 are on the exam, because the exam technically covers 4, 5, 6, 7, and 8. So what should you be prepared for? There will be some questions about substitution and elimination on the exam. It won't be the whole thing. If anything, it will be stuff about SN2 and E2, which we have covered mostly. I am deciding right now to hold off on the SN1 and E1 questions. You'll face them soon, but not this soon, maybe. No, I will promise you not to put SN1 and E1 questions on the exam. I think that's what I can say, all right? All right. With that in mind, I understand some of you may wish to come and ask questions and the 9 o'clock hour doesn't work for you. Today, I will be around in my office from 3 to 5 too, if you want to drop by and ask questions then. Yes? Will there be a TA review? I always forget to talk to the TAs about this, but some of them usually do it. So stay tuned. When there are ones scheduled, they will let you know. Sorry, that's not a great response. Yeah. Yes? Is it going to be all multiple choice? Yes, it will be all multiple choice. You want instant feedback and I don't want to grade them. Yeah. What's the answer to question 1? It's either R or S, or not a stereo center. Is that helpful? Yeah. Hold on. I got it here. Okay, go ahead, Isabella. Oh, yeah. So in the key to the practice exam, you may be wondering, suppose the products of a particular reaction were, suppose they were as follows. One way to communicate that you get both stereoisomers, or rather both configurations at a stereo center, is to simply not use dashes and wedges, but just use that. You got to know what you're doing when you do that, because the organic chemist looks and says, that is an sp3 hybridized carbon. I know it's tetrahedral even though it's drawn that way. That is a stereo center, but they didn't show me whether it was coming out of the page or back towards me. Therefore, they must be communicating that I have both configurations of that stereo center. So that is something you can do. You have to be a little bit careful with it. I think we talked about a potential example once where if these were the products of the reaction and you, draw the same thing twice, and you tried to draw the products like this, that would be okay here, but not okay there, right? Because you don't have both configurations of the stereo center here. So just be careful. You don't have to use dashes and wedges. If you want to be succinct and communicate both configurations at a stereo center, that's fine. Just make sure you do it right. Yeah?
But even if the molecule ends up being achiral, the product, you still have a racemic mixture.
If the molecule is achiral, it's no longer called a racemic mixture because they're not, there's no enantiomers. Yep. Okay. So, let's continue where we were on Friday. we were talking about how substitution and elimination compete. We've dealt thoroughly with SN2, which is nucleophile attacks as the leaving group leaves. The things that are going to promote that are having a good nucleophile. A good nucleophile is not going to wait around for the leaving group to leave first. Okay? So, however, you also have to consider the characteristics of the alkyl halide leaving group. Is it primary, secondary, or tertiary? And we've seen that because of backside attack, the SN2 reaction doesn't happen for tertiary alkyl halides due to steric hindrance. The nucleophile simply cannot access the alpha carbon. Fast for primary alkyl halides and of reasonable speed for secondary. So those are your two considerations. If you don't have a good nucleophile, you're probably not going to go this direction. And if you have an alkyl halide that's tertiary, you're also not going to go this direction. Now, the elimination direction is favored by good bases. And so a good base isn't going to wait around for the leaving group to leave before it removes a beta proton. We've said that the trends for speed of elimination are backwards from those of substitution. So, for example, E2 is fast for tertiary alkyl halides. And part of this is because tertiary alkyl halides simply have more beta protons. But the other part of it is we're going to see in just a minute that tertiary alkyl halides lead to more substituted alkene products, which are more stable. And because the transition state of the E2 reaction has a lot of alkene character, transition states that lead to more substituted alkenes are going to be lower in energy and accessed faster. So E2 is slowest for primary alkyl halides, moderate for secondary, fast for tertiary alkyl halides. So if, for example, you were dealing with a tertiary alkyl halide and a molecule that was both a good nucleophile and a good base, you can't go to the right because of sterics, so you're going to go this way down the E2 pathway. Okay? That's sort of how we're going to reason things through. Now, today I want to talk about how you know when things are going to happen in terms of the SN1 pathway and the E1 pathway. And I want you to understand that in the SN1 reaction, as you've learned, the leaving group leaves first before the nucleophile comes in. You get a carbocationic intermediate. And once you get to that intermediate, you have a couple of different choices. One is for a nucleophile to attack the alpha carbon. The other is for a base to remove a beta proton, that is, a proton adjacent to the positive charge in the carbocationic intermediate. What we're going to see up here for the concerted reaction, there was selectivity, right? We could have a molecule that would act as a good base and you would only get elimination products. You could have a molecule that was a good nucleophile and you get only substitution products. We're going to see no such selectivity for the carbocationic intermediate. There's reason for that. We'll talk about it in terms of the energy diagram. So we will see that SN1 and E1 always compete. There may be things in specific cases you can do to bias it towards one versus the other. We are not going to care about them. We're just going to be anticipating both possibilities if we have a carbocationic intermediate. Okay? Finally, remember in the back of your head that there are stereochemical issues associated with the SN2 reaction, inversion of configuration, and with the E2 reaction, the requirement that the beta proton be anti to the leaving group. And your understanding of stereochemistry, I can use stereochemistry as a way to tell how well you understand the SN2 and E2 mechanisms. We're going to see that there are stereochemical issues associated with these reactions. For example, the SN1 reaction, you get both configurations. All right. So let's talk about this first step of the SN1/E1 pathway. That is where the leaving group leaves. And we sort of started to talk about this last time where I said, how does a leaving group leave on its own? And the answer is It's very slow because it's a step that just involves bond breaking. I told you that bonds vibrate like springs, and if the molecule gets enough kinetic energy by bumping into other things, you can excite that vibrational frequency to the point that instead of just sort of going back and forth in terms of distance between carbon and iodide here, you get enough energy to get up here, and at that point the spring breaks and the iodide goes off to infinite distance, and you're left with a carbocation. All right. So how do you know when that's going to happen? That step is slow. In energy diagrams, you would predict that forming a carbocationic intermediate from some starting material like this would be really slow because all you're doing is breaking a bond, right? I'm running out of space, so we'll just go down here. So when is that going to occur? And often the answer is when nothing else can. So, for example, we will see that for a tertiary alkyl halide, it doesn't matter if you have a good nucleophile. Suppose we use azide, which is a good nucleophile. You can't do SN2 at a tertiary alkyl halide. And this is a good nucleophile, but a weak base. So you can't do E2 either. Having ruled out both of those, what can happen is then the SN1/E1 pathway, which means we have to sit around and wait until we break the spring and get a carbocationic intermediate. So we will show that happening by the leaving group leaving. And that's an uphill, very slow rate determining step, RDS, and here's the carbocation. And then and only at that stage can the chemistry happen. Now, I want to pause here because I want to talk more about this first step and when it's viable and when it's not. I gave you one situation where you can tell it has to happen because SN2 isn't an option and E2 is not an option. Yeah?
So you said that the SN1, E1 only happens when nothing else can. Is that just because the SN2, E2 reaction is just so much more quicker and favorable?
Yeah, SN1 and E1 only happen when nothing else can because the other options are more favorable. Rather, if you have, the other options are more favorable if they're possible. I think that's two ways of saying the same thing, which is actually not helpful. So good nucleophiles will favor SN2, good bases will favor E2, but you also have to mix into that the alkyl halide structure. Yeah?
Someone might have already asked this, but in terms of like for N3 and we have a pKa value for...
Would I give you a pKa value for N3? Probably. Its conjugate acid is HN3, which has a pKa of like 9. By experience, you'll come to recognize that as a good nucleophile, though. All right. So understand that this is a situation where we had a good nucleophile, so SN2 would be great, except the alkyl halide structure prevents it, right? Okay. Let's talk a little bit about this carbocationic intermediate. Yes?
Just making sure, if we have a primary alkyl halide with a strong base and a strong profile, do you only want to show us N2?
Sure. If you have a primary alkyl halide and a molecule that's both a good and a molecule that's both a good nucleophile and a good base, you're going to show just the substitution products because it's fast for SN2 but slow for E2. All right, let's talk about the carbocationic intermediate. We are going to see that carbocation stability depends on how many non-hydrogen groups are attached to the positively charged carbon. Understand that stability is a relative term, so none of these carbocations is very stable, but we're going to see that the ones that have more non-hydrogen things attached to the positively charged carbon are more stable than those that do not. Okay? So we're going to see, for example, that tertiary and secondary carbocations are going to be okay as intermediates in reactions, whereas primary and methyl carbocations are generally not good intermediates in reactions, at least not reactions in the solution. All right, and there's a reason for that which we will talk about, but I just want to give a bit of a warning because there's a situation described on your practice exam that I think is confusing to people, but it's not as bad as you think once we think about it. Yeah?
Just really quickly, is the reason that less hydrogens means less stability because there's greater opportunities? I guess less hydrogens means more stable because there's greater opportunities for electron sharing?
Less hydrogens means more stable because there's more opportunities for electron sharing. Sure, let's actually talk about that right now. Notice if we call the carbocation the alpha carbon, notice that the more substituted tertiary alkyl halide has more beta protons. So what on earth does a beta proton have to do with the stability of a carbocation? Well, remember that delocalization of electrons is a favorable thing. And if you have a positively charged carbon, as I think we began to talk about last time, the LUMO, we would say, is the empty p orbital on the positively charged carbon, which has lobes above and below the plane of the carbocation. And in a tertiary carbocation, you have all of these adjacent carbon-hydrogen bonds. I'm going to only draw sort of one of the carbon-hydrogen sigma bonding orbitals, but you have a filled carbon-hydrogen bonding orbital, and it's lining up with an empty p orbital. And so this is a situation where you can get what's called sigma to p hyperconjugation. Remember, we're using hyperconjugation as a way to bridge our understanding from sort of valence bond theory to what the results of molecular orbital theory tell you. MO theory actually tells you that the LUMO of this molecule is not only the empty p orbital, but is also on adjacent protons. Right? So, and how do we conclude this? Well, if you mix that empty p orbital with a sigma bonding orbital, you're going to get the plus combination that's lower in energy, and the sigma bonding orbital is where the electrons were. The plus combination will allow those electrons to move a little bit lower in energy and to spread out a little bit towards the carbon. And then up here we'll get an anti-bonding type orbital. This is the minus combination of the sigma with the p orbital. This will be the LUMO moving a little bit higher in energy and spreading out onto those adjacent atoms. The plus combination, I'm just showing the view of one of the adjacent carbon-hydrogen bonds. The plus combination would have the two coming together with the same wave function sign. If you sort of squint and look at it from the side, this begins to look a little bit like a pi bond, partial sort of pi bond character, as electrons in the carbon-hydrogen bond spread out and occupy both of these spaces. Whereas the LUMO the minus combination looks like, oops, let's try that again, looks like this, where there would be a node in between the carbon-hydrogen bond and the p orbital, but some of this LUMO is out on the adjacent proton, all right? Hyperconjugation is stabilizing because it allows these electrons to move lower in energy. Hyperconjugation is stabilizing. So it would make sense that the more beta protons you have that can line up with the empty p orbital, the more stable the carbocation should be. So you can memorize that tertiary carbocations are more stable than secondary, which are more stable than primary, which are more stable than methyl, but it's better to know why. And the reason why is there's more opportunity for electron delocalization when you have more beta protons. Okay, anything you want to ask about that? Yeah.
And would you call that constructive interference?
Of these electrons moving lower in energy, yeah, this would be the constructive interference or plus combination. The fact that the LUMO spreads out is the minus combination issue. But you can see, we're going to use this picture as an explanation for why we have to worry up here once we get to the carbocationic intermediate, why we have to worry about both substitution or elimination reactions. The SN1 reaction occurs as we attack the alpha carbon, whereas the E1 occurs as we attack the beta proton. Why do you have to worry about both? Because the LUMO is in both places. It's both on the alpha carbon and on the beta proton. All right, so carbocation stability is important because this is an intermediate in the reaction. Now, we're going to see because of this that the rate of this first step is going to be faster for the more stable carbocations and slower for the less stable carbocations. And the reason for that is allows us to illustrate a general principle in organic chemistry that's named after the person who first sort of described it, and this is the Hammond postulate. I'm writing it here not because we really care about the names of folks that did stuff, but rather because your text will refer to it, and it's not as bad as it seems. The Hammond postulate says that on an energy diagram, two adjacent we'll say positions. By that we mean like an intermediate, starting material, a product, or a transition state. Two adjacent positions that are close in energy must necessarily be close in structure. This means that on our energy diagram, this intermediate that is a carbocation is close in structure to the transition state, and therefore they're adjacent to each other. There must be a lot of similarity between the structure of the intermediate and the transition state. Or in other words, if I were to ask you, is this transition state more like the alkyl halide starting material or more like the carbocationic intermediate? The answer is it's more like the carbocationic intermediate because they're close in energy. All right? So let's see what we would predict on an energy diagram for, we've got starting materials here, and we'll give primary alkyl halide, secondary alkyl halide, tertiary alkyl halide. The intermediate is going to be up here. It could be the tertiary carbocation, or the secondary carbocation, or the primary carbocation, which I'm going to draw here. Okay, so we're going to assume that in terms of starting materials, they're all basically the same energy. But we've just established that in terms of intermediate energy, the tertiary carbocation is more stable than the secondary carbocation, which is more stable than the primary carbocation. So if I'm going to connect these the starting material with the intermediates here, which do you think has the highest energy transition state? The primary one. It's almost boring, right? Like it's sort of what you expect because the transition state has to resemble the position that it's closest to in energy. So the transition state that leads to the primary carbocation is going to be very primary carbocation-like, which means that the transition state leading to the primary carbocation is going to be more unstable than the transition state that leads to the secondary carbocation, which is going to be more unstable than the transition state that leads to the tertiary carbocation. That makes sense? So the rate of SN1/E1 depends on the alkyl halide structure in the sense that it's reasonable for tertiary and secondary alkyl halides, but the transition state is too high in energy for the primary alkyl halides. Yeah?
So going back to hyperconjugation with the leading group, so how come when it's a third degree, we talk about the leading group being first, when it's first degree doesn't? Because when I think about hyperconjugation, more beta protons be stabilizing the leading group more and keeping it closer into the molecule itself.
So I think you're talking about hyperconjugation in the molecule that has the leaving group still attached. And I think you're envisioning that a tertiary alkyl halide is going to have more chances for sigma to sigma star hyperconjugation. And you're right. That should spread out the LUMO onto a lot of those adjacent beta protons. Now, if you want to think about hyperconjugation as though it were dumping a little bit of electron density into the sigma star, then you might predict that this bond would be longer and weaker than for molecules with less adjacent beta protons. And I believe that's true. But yeah, and remember that hyperconjugation describes the stability of the electrons in the adjacent carbon-hydrogen bonds spreading out, not necessarily the stability of the electrons in the bond with the leaving group on it. So I think it's reasonable that the hypothesis that, yeah, if I have more beta protons, more things are dumping into the sigma star, that ought to make this bond longer, and that's actually a pretty reasonable line of thinking. And that might also explain why the leaving group leaves better from the tertiary alkyl halide, because you're already, you could imagine these adjacent beta protons sort of helping to kick the leaving group off. Yeah. All right. So because of this, we're going to say that in general, SN1 and E1 rates, now they're always slow, right, because they always involve bond breaking, but we're going to say for the SN1 reaction, we don't really see this working for primary alkyl halides. It is slow for secondary alkyl halides, and it's less slow for tertiary alkyl halides. We could say no reaction, slow, and fast, but I don't want to communicate that the SN1 reaction, SN1 and E1, first step, leaving group leaving, is fast, because it's not. It's slow. But it will be faster or less slow for tertiary alkyl halides than for secondary alkyl halides. Yeah?
Why is there not an option with 2 hydrogens?
Sorry. And I could put methyl on this list and it would be even higher, but let's just not. Sorry, that was my bad. All right. Now, here's an interesting controversy, perhaps. I don't know. Controversy may not be the right answer for this. What kind of alkyl halide is that? If you just memorized it, you would say this is a primary alkyl halide, and you would say, if you just memorized, you're going to say there's no SN1 and E1 based for that starting material. And you will get a question wrong on the next exam, not because I promise not to put SN1 and E1 questions on this exam, but on the next one. You will get a question wrong if you look at that and you say, no, SN1 isn't possible for primary alkyl halides. You'll get it wrong because you've forgotten that the issue with primary alkyl halides not doing SN1 is related to the stability of the carbocationic intermediate. So I want you to consider the stability of this carbocationic intermediate versus the stability of this carbocationic intermediate. Do you expect those to be the same in terms of stability? No. What's the difference? Resonance stabilization. Yes. So resonance stabilization makes this carbocation feel like it is not actually a primary carbocation. And you can actually do experiments that verify this. You can measure something called hydride ion affinity, which describes how much a carbocation wants to attract a nucleophile to attack it. And a resonance stabilized carbocation like this, even though it's primary, is about as stable as a secondary carbocation. So we're going to see that we would say, yeah, there's no SN1 and E1 for this one, but for alkyl halides where there is the possibility of resonance stabilization, we're going to see that SN1 and E1 are okay. All right? So be careful with that, because you're gonna if you don't look for the possibility of resonance stabilization in the carbocation, and you just memorize that primary alkyl halides there's no SN1 or E1, we're going to have this conversation again in my office, and you're going to say, you said, and the book said that there's no SN1 and E1 for primary carbocations, and I'm going to say, what about resonance stabilization? Okay? You have been warned. Right. So, I think, yes?
So can you just treat that as if it was a secondary carbocation?
Yeah, you can treat it as though it were a secondary carbocation. Other hands, same question? Go ahead.
What would an exam question look like that one might get wrong?
I like how you think. What would an exam question look like that one might get wrong? We've only talked about the first step of this reaction, so I suppose I could ask a question like this. Let's just do... And there might be a list of products here, and one of the options J, or maybe K, because that's all the testing center will let me get to, might be no reaction. Dummy. That's you saying that to me, right? No reaction. And if you chose that, you would get that wrong. Why would no reaction not be the right answer? Well, or why would you be tempted to think that? You would see that this is a weak nucleophile and a weak base. So SN2 and E2 are not options. It's if you just memorized stuff, you would think that that's a primary alkyl halide. And so you might say, yeah, carbocations are not reasonable for primary alkyl halides. So no reaction. However, you should not ignore the possibility for resonance stabilization in the carbocationic intermediate. And the structural pattern you want to look for is an allyl halide. What do I mean by allyl? Well, we have ways of talking about this molecular structure for double bonds. This is the vinyl position, and this is the allyl position. So a molecule with an alkyl halide attached to the allyl carbon is called an allyl halide. So allyl halides, you're going to treat like secondary/tertiary alkyl halides in terms of their stability. Is SN1 possible here? Sure. I'm sorry. Is SN2 possible here? Can you do a backside attack with a good nucleophile? Absolutely. Okay, sterics is the major issue there. But is SN1 and E1 possible? Yes, because I suppose, yeah, you should categorize it as sort of like a secondary alkyl halide. But yes, because once you make the carbocation intermediate, it's stabilized by resonance. Yeah?
Can it attack from both carbocations, or will it want to attack?
Can what attack from both carbocations?
A nucleophile, for
Can a
example.
nucleophile attack from both of these carbons? We'll call them, I don't know, 1, 2, and 3. Well, let me ask you this. Are those two separate carbocations? What does resonance mean? It means the plus charge is at both positions. So yes, indeed, a nucleophile could attack at either position. Is one going to be more favorable than the other? I don't know. So you draw both. Yeah?
And this concept would apply the same for vinyl halides?
Would this concept apply the same for vinyl halides? No. So here is a vinyl halide. If the leaving group left, by the way, this is a very bad step. If the leaving group left, in fact, you now have a carbon that's only attached to two things. What can that positive charge be stabilized by resonance? No, it really can't, and the reason for that is the carbon that has the positive charge is already involved in the pi bond. There's no place to push the electrons that would make the situation any better. Okay? So actually, your text has mentioned this, but we're going to see that carbocation intermediates basically are terrible when the positive charge is at an sp2 carbon. So generally, we don't see these kinds of things for vinyl halides, and we also don't see these kinds of things for like aryl or benzene ring halides, because you got the same issue. The plus charge there can't be stabilized by resonance. So these are really bad intermediates. And so, yeah, we're gonna not do SN1/E1 chemistry on these. Yeah.
So, on that, would you end up with a racemate mixture on carbon 1 and 3?
Right, so on carbons 1 and 3, remember that once we have a weak nucleophile that's a weak base, so once we get to that carbocation, we're going to envision both SN1 and E1 products. For the SN1 products, the nucleophile is going to attack from above or below at any place where there's a positive charge. Just so happens that in this case we wouldn't be making a stereocenter, so there's no stereochemical issues to take care of. One substitution product would be this one, and the other substitution product would be this one. If those were stereocenters, then yes, we would show both enantiomers. Those are the substitution products. And what would the elimination products be? Well, for that, I need to look at either of these carbocations, and I need to find beta protons that can line up with the positive charge. So here, I've got two different beta protons that can line up with the positive charge. Some of you are going to say, what about this one? Can that one line up with the positive charge? The answer is no. Why? Because this proton is held perpendicular to the pi bond, right? That's just molecular structure. And resonance involves this pi bond lining up with this positive charge. If we rotate around this bond to get this proton lined up with this positive charge, you have to break resonance. The pi bond will no longer be conjugated to that positive charge. So because of that, this beta proton, the one that's on carbon 2, will never be in a position to be removed because it can't line up with the positive charge. Does that make sense-ish? Yeah?
Goes back to the idea that for elimination reactions,
It's related to the principle in the E2 reaction that only protons that can be anti to the leaving group are reactive. Similar principle here, it's only protons that can line up with the empty p orbital can be reactive. So we're not going to worry about this proton. Instead, we'll worry about those two. Thankfully, they're identical, so the elimination products from that carbocationic intermediate is just this. And we don't need to worry about elimination from the other carbocation for the issue that we just talked about. That proton on carbon 2 can never line up with a positive charge. So I would have shown you these three options among others, and I would given you the instructions to this problem would have said select all that are products of this reaction, and you would need to select A and C and F, but not K or any of the other bogus options. Yeah.
Will this lining up only occur with an anti-paraffin arrangements like E2 or no?
Will the lining up of a beta proton with a positive charge only occur with anti-arrangement? Well, once the leaving group is gone, there's no issue with anti-periplanar because you can see this proton could line up with this p orbital either on this side or on that side. It's just this unique case where because of resonance, a proton is sort of permanently orthogonal to the place where the positive charge is. All right. Mechanism-wise, let's talk about the SN1 and E1 reactions. When you get that carbocationic intermediate, what happens to it? So for that, we're going to just use this as our, which we're remembering as our LUMO. So if this is our intermediate, if we have our nucleophile slash base, let's use methanol, which is a weak nucleophile and a weak base. If it attacks at the alpha carbon, that gives us substitution products. In this case, we would not be making a stereocenter. when you have an alcohol attack positively charged carbon, you end up with another intermediate where you have an oxygen that's attached to 3 different things. Because the pKa of that proton should be around -2, it seems reasonable for another molecule of methanol from the solvent to remove the proton to give you the neutral product. And so we're going to draw the neutral product as the product of this reaction. And then the other thing that's available to us is if that alcohol, instead of attacking the alpha carbon, attacks the beta proton, then these electrons would move to form a new pi bond, and we would get that as our elimination product. So this is the product of E1, this is the product of SN1. What we are saying, by the way, when we're saying that these 2 options always compete, that's just another way of saying the barrier from this point to go down the substitution slope versus the elimination slope is about the same. So there's no selectivity. It's about as hard to go over one slope as it is to go over the other one. All right? So what we need to do is take all of this together and summarize it. There's a couple of ways to do this. One is through an energy diagram like this, which I'm going to try to draw for you next time, where we actually show you the 3rd dimension. And then the other way is through a chart that you're sort of a decision-making table that your, I think, study guide takes you through in terms of what the consequences of the reactions are going to be. Let me just, let's see, got a couple of minutes. I will give you a sense for what this table will look like. You'll have, across the top, you'll have nucleophiles, so things that are good nucleophiles / good bases, things that are good nucleophiles but not good bases, things that are weak bases but, oh, whoops, already did that one. Things that are weak nucleophiles but good bases, and then things that are both weak nucleophiles and weak bases. And here you'll have primary, secondary, and tertiary alkyl halides. And then you're just going to go through each of these 12 situations and reason through what the consequences should be based on what you know about the rate of the SN2 rate of these reactions, how it depends on alkyl halide structure, and then what you know about how the good nucleophiles favor SN2 and good bases favor E2. All right, seems like y'all are ready to go, so be gone with you, and we'll see you next time.